our speaker today is Stefano Ermon, the assistant professor in the Department of Computer Science at Stanford University, and affiliated with the Artificial Intelligence Lab and the Woods Institute for the Environment there. And his research is on probabilistic modeling and inference in machine learning and computational sustainability. And he's going to talk today about things related to his Future of Life Institute grant on accuracy guarantees for probabilistic inference. So join me in welcoming Dr. Stefano Ermon.
Yeah, thanks for the invitation. It's great to be here. I put together some slides about some of the work we've been doing on this topic, about developing robust probabilistic inference schemes. But since it's a small crowd, if you have questions, you want me to focus more on some topics or the other, just ask me and I'm happy to sort of steer it in whatever direction you want me to go into. So in the past 20 or 30 years, we have seen a lot of progress in terms of combinatorial search and optimization technologies. Solvers for problems like satisfiability testing, mixed integer programming, constraint programming. Solvers in the early 90s were able to handle very small problems with a few hundred variables, a few hundred constraints. Nowadays, we can solve very large industrial instances with up to millions of variables and constraints. So just to be clear about what I'm talking about here, I'm thinking about problems like satisfiability testing, where we're given a formula, so a set of constraints, and we are trying to figure out whether there exists a way to set the variables such that the formula evaluates to true. So we could have something like this, where we have three constraints saying that x1 or x2 or not x3, and not x2 or not x1, and so forth. And the problem is trying to figure out a way. So we have a set of equations, basically Boolean equations, and we want to figure out if we can assign truth values to these variables so that all these equations are satisfied at the same time. So this is the canonical sort of NP-complete decision problem, and it has found an enormous number of applications. Like this idea of using a symbolic representation for the problems we care about, and then using one of these state-of-the-art solvers to try to solve this kind of combinatorial optimization or decision problems, has found a very, very large number of applications in the past 20 or 30 years. So these applications range from scheduling problem, hardware and software verification, network design, program synthesis, game playing, and many, many more. So this is, I would say, an example of a very successful paradigm that we have in AI. This idea that we know there are a lot of problems that we care about, that we want to solve, like hardware and software verification or game playing and so forth, that are very domain specific. But instead of trying to develop algorithms that are very specific for these particular problems that we care about, a very successful idea in AI is this paradigm where we should separate as much as possible the modeling, the models that we use to define these problems, and the algorithms that then we use to try to solve these problems based on the models that we came up with. So this idea of sort of separating the models from the algorithms as much as possible has been very successful. It's good on several levels. It's from an engineering perspective, it's good to have this separation, to have a modular system where we have general modeling languages, general algorithms, because if we can come up with better, say, reasoning algorithms like SAT solvers or integer programming solvers or things like that, what it means is that you can, the benefits basically propagate to all the problems that you can encode in that modeling language. And also sort of from a philosophical perspective, this idea of having a general reasoning engine that can handle all sort of problems that can be formulated in that language is in some sense, is going in the right direction towards building a real AI system, like a general algorithm, a general system that can sort of handle all sort of problems that we care about. So the question is, what is the right modeling language that we should use? And essentially the model is what we use to represent the knowledge that we have about the particular domain we care about. So the simplest form of knowledge that we might care about is completely deterministic. Something like if there is rain, then there are clouds, which you can, for example, represent this implication. You can write it in the sort of language we used before in the context of SAT, that's something like this: clouds or not rain. So this is the simplest kind of knowledge we might be interested in using, and it has a lot of potential applications. But sometimes we want to include, it's not always, there are situations, there are real-world problems where, the kind of knowledge we have includes some form of uncertainty. For example, we might want to say something like, if there are clouds, then there is a chance of rain. And taking a step further in this direction, sometimes we might be interested in knowledge that is probabilistic. So we might want to be able to say something like, if there are clouds, then there is a probability of 20% that it will actually rain. So depending on the kind of application problem that you have in mind, one of these languages might be more or less appropriate. And the ability to handle uncertainty is particularly useful in a lot of domains, because it basically allows us to handle noise, ambiguities that often come up if you think about natural language, or there could be noisy measurements, or there could be sensors that we have to deal with that will not give us an exact answer, or there might be quantities that we don't get to observe. So in many application domains, it's very important to be able to handle uncertainty if we want to build robust systems. And this idea of sort of embracing uncertainty and using probabilistic models has had a lot of impact in AI, and it basically opened up a whole new range of applications, including essentially a lot of the new machine learning applications are based on this idea of modeling the world using random variables, using probabilistic models. So, there are lots of applications of these ideas in computer vision, natural language processing, robotics, bioinformatics, social sciences, even in ecology, and many more. The question is, how do we represent probabilistic knowledge? And the one powerful framework to represent probabilistic knowledge is to use, say, graphical models. Here the idea is that we represent the state of the world using a set of random variables. In this case, I have 3 of them, representing the fact that it's raining, the grass is wet, and the sprinkler is on or off. And then we define a probability distribution over the possible states of the world. And basically what we want to do is we want to be able to specify for each possible assignment of these variables, so for every possible state of the world, we want to specify a probability for that particular state of the world. And this can be done compactly using, say, factor graph formalism, which is basically, you can think of it as a set of soft constraints on the possible values that the variables can take. And instead of saying something like, if it rains, then the sprinkler is off, you could sort of do it probabilistically by saying, well, if it rains, then it's very likely that the sprinkler is off, then on. That's sort of the intuition. And you can combine many of these soft constraints, and by putting them together, you get a probabilistic model that will basically specify for each state of the world the probability given by the model. And for example, in this case, the semantics, it's not very important, but the idea is that you get the probability for a full assignment for a state of the world, say a state of the world where it's raining, the sprinkler is on, and the grass is wet, and you get it by basically taking a product of the corresponding entries in the tables. So the key idea is that our knowledge about the world is represented using some soft constraints or some soft dependencies among the variables, which you can think of it as some kind of weighted version of the satisfiability problem we had before, where the constraints were kind of hard. It has to be the case that if it rains, then the sprinkler is off. So how do we do reasoning in these kind of models? Well, the basic probabilistic reasoning problem that we want to solve is that of computing probabilities of events. For example, we might want to compute what is the probability that the grass is wet, and basically by definition of the the standard rules of probability, you can compute this marginal probability by integrating out the joint probability distribution over all possible states of the world in which the grass is wet. So you have to sum up the probability of all possible states of the world in which the grass is wet, and you get a number. Now, this joint probability is specified by the model, and so this is well defined. It's a computation that you can try to solve. So you can see that this kind of computation, this kind of probabilistic reasoning problem, involves some form of model counting, weighted model counting, where you have to look at all possible states of the world or possible models, and you kind of have to sum up their probability or something that is close to a probability. So if we had hard constraints, so if, remember here, if the constraints that we had were hard, something like, let's see, it has to be the case that when it's raining, then the sprinkler is off, then this probabilistic inference query would correspond to an unweighted model counting problem, where you basically would have to count the number of states of the world that satisfy all the constraints in the problem, such that this variable, the grass, where basically the grass is also wet. And while if we have soft constraints, if we have constraints of this form, then this becomes a weighted model counting problem where you have to sum up the weight of all possible assignments of the variables, all possible states of the world in which the grass is wet. So this is the basic probabilistic inference problem. And we can still think of this problem into this sort of setup where no matter what kind of particular problem you care about, whether it's computer vision, whether it's from NLP, you can still formulate the problem into this modeling language, which is the language of graphical models. And then the idea would be to have some kind of general reasoning engine that can take the problem once you have specified it into this modeling language, and it will give you a solution. In this case, it will solve, say, a probabilistic inference query.
Just a quick question.
Yeah.
The model I can write about the blue thing, that one is usually done by humans, like generally.
Yes. That's the modeling part, and that involves human intervention, yeah. And that's hard. An interesting thing to notice here is that when we're dealing with the deterministic knowledge bases, like where the constraints are hard, it has to be the case that if it rains, then the sprinkler is off. And if we think about the kind of reasoning engines that people have built for this kind of knowledge bases, soundness is always critical, is always very important. If you think about satisfiability testing, SAT solvers or SMT solvers or proof assistants, people care a lot about building systems that will give you the right answer. Like, if you give it a set of constraints and it will say this is satisfiable or is not satisfiable, you really want it to be the case that the answers that you get from your reasoning engines actually make sense, that is actually correct, it is computing the right thing. Nobody, if you build a SAT solver and they say, oh yeah, I think it, sometimes it gives the right answer, sometimes it doesn't, people wouldn't be very happy. On the other hand, in terms of probabilistic reasoning, a lot of the emphasis in terms of what people have been doing in the community has been much more on the scalability of these algorithms, making sure that this reasoning engine can handle very large problems with lots of variables. But there has not been so much emphasis on developing reasoning engines that will actually have pretty reasonable kind of accuracy guarantees. That we would like to make sure that whatever answer we get from this green box, it is related, it is pretty much what we actually want. If you're supposed to compute a marginal probability, we would like it to be close to what we actually, it's supposed to compute. But that's not always the case. A lot of methods like Markov chain Monte Carlo methods, they typically don't have strong accuracy guarantees. Variational techniques, we're going to talk a little bit about that later. They also don't have strong accuracy guarantees. And, you might think that since we're modeling the world probabilistically, it's not that important that we actually compute answers exactly. And in fact, I think in most applications, it's actually okay if there is a little bit of error in the answers that we compute using these reasoning engines. For example, if you're trying to compute what is the probability that my autonomous vehicle is going to hit a pedestrian or something, if instead of computing maybe the right answer is 0.546780, and we compute maybe 546781, in most applications that should probably be okay. But on the other hand, we want to make sure that something like this cannot happen, that the probability according to the model is 001, but actually because our reasoning engine has no guarantees on the accuracy, maybe it says 0.96. That's not something we want if we want to build robust systems that are based on probabilistic models. And unfortunately, a lot of the existing techniques like Monte Carlo sampling methods and variational methods, they don't give you this kind of guarantees. Like you run this green box, but you don't really know, you might get a number, you can get 0.96, but you have no idea whether the true number, the number that you're looking for, is really something close to 0.96, maybe 0.961, or it could be 0.01, and you have no way of detecting that. So that's the focus of my FLI grant is basically on developing general reasoning engines that have accuracy guarantees. So coming up with new techniques, new ideas to develop algorithms that are closer to the ones we have for deterministic knowledge bases. Whenever they spit out an answer, we know that it's closely related to what we actually wanted to compute. Questions on the sort of broad picture of, yeah.
So you want a probability, basically one chance of having bounds on each answer, or do you want to have a epsilon chance of being far away, but that being good enough?
Well, ideally, you would like a little error on the probability. So if, there is you can say, ideally, I would like to have a parameter here that you can sort of choose, and it will control the accuracy of the answer you get.
So basically, do you want PAC probabilities? Probably approximate.
Yes, something like that. Or even better, maybe something deterministic that is guaranteed to give me an answer within that error bar, which is what you would normally do. Say if you have like some numerical linear algebra problem, you say I want an answer with this tolerance, give me an answer, and the contract is whatever your algorithm outputs is going to be within that tolerance.
Okay, but you're looking at both PAC and deterministically bound there. My methods are actually PAC, so there is a probability of failure, which you can control and you can make it small. But ideally, I think it would be even better if we could do it, deterministically, just like sort of numerical linear algebra, where you say, okay, you have a tolerance, you specify it, and then you're going to get an accurate answer. And then there's, of course, going to be some kind of trade-off between the computational complexity and the accuracy, and that's something that you have to explore empirically, and it might not be possible to get, if you think about having an autonomous agent that is using this kind of techniques, it might be, and if you have to take decisions in real time, there's going to be some kind of trade-off between, you might not have an unlimited computational budget, and so there could be interesting decisions to be made there in terms of how do you set the accuracy level. But ideally, I think it's important that we think more about getting accurate answers rather than just thinking about, okay, let's handle larger and larger problems, but without really knowing what we are computing at the end of the day. Okay, so just to keep things simple, I want to describe the algorithms that we've developed in the simplest possible case. So where we basically don't have weights on the possible states of the world. So in the deterministic reasoning problem, we're given a formula like this, and the standard task, the satisfiability testing task, is trying to figure out how to set the variables so that the formula is true. We've seen that the basic probabilistic reasoning problem is
essentially some kind of model counting problem where you have to look at all possible scenarios, all possible states of the world, and you effectively have to count how many possible states of the world there are that satisfy a given formula F. This is kind of the canonical probabilistic reasoning problem. And so, you're given a formula basically, which specifies your knowledge base, what you know about the world, and you want to count how many different ways there are to set the variables so that that formula evaluates to true. For example, you can set true, false, true in this case, and it will satisfy that formula, because this is, I guess this one is satisfied by the true, this one is false, so it's satisfied, and this one is satisfied, or you could set false, 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 and that would also satisfy that formula. And the problem is figuring out how many there are. If you had weights, then you would basically have to sum up the weight of each possible world, but just for simplicity, let's just think about a scenario where all possible worlds are either possible or not possible, and we just want to count the worlds that are possible. So, how hard is it to do probabilistic reasoning with respect to deterministic reasoning? Well, you can immediately see that counting how many different satisfying assignments we have is going to be at least as hard as deciding if there exists at least one, right? If you can count how many you have, then you can just check whether that number is 0 or non-zero, and so you know whether there exists at least one or not. So it turns out that model counting is sharply complete, which is a complexity class that is believed to be even harder than NP. And even in practical terms, doing model counting is typically hard for several reasons. The first one is that often even finding a single solution is quite hard. Like satisfiability testing, it's NP complete, and we believe it's hard in the worst case, and even in practice, even though we have these very good solvers, it can be hard. Yeah?
I'm sorry, could you give a short definition of sharply?
It's essentially the problems where you're given, there's kind of two versions, but the idea is that you have to count the number of accepting paths of a Turing machine. Sort of. That will be one. The challenge is that, as usual, we're dealing with huge search spaces. So if you have maybe 1,000 variables, then you have something like 10 to the 300 possible truth assignments. So it can be of course you cannot explore it by brute force, and it's often the case that these solutions are kind of sprinkled around unevenly in the space, and so that's what makes, say, sampling hard. Like if you just randomly pick an assignment to the variables. Say, imagine that we're in this scenario where we have 10 to the 300 possible truth assignments, and then you randomly pick one of them. Even if you have something like 10 to the 60 solutions, which is a huge number, the probability that you're hitting a solution by picking an assignment at random is going to be something like 10 to the minus 240. So it's going to be a tiny number. So that's why it's hard, because the space is huge and the density of solutions can be extremely small. And it's very hard to figure out whether you have a lot of solutions or no solutions at all. So let me go through a few possible approaches for solving this model counting problem. Let me try to describe it using an analogy. Instead of looking at the problem of counting the number of solutions, we're going to think about the problem of counting how many people there are in, say, a lecture hall. And this problem resembles a lot the model counting problem, in the sense that, like in a model counting problem, the space, say if you think about a lecture hall, has some structure. It's naturally divided, say, into rows, columns of seats, sections. It's similar to the counting problem in the sense that many seats, say, could be empty. And there is an uneven distribution of people in the lecture hall. So maybe there are more people close to the exits or near to the aisles. So that's sort of the intuition that something, a pictorial representation that might be useful when you think about model counting problems. So sort of the analogy is that if you have a formula with n variables, we have an auditorium, which is the search space for f. Each seed corresponds to a possible truth assignment to the n variables, and there are, say, if the variables are binary, we have 2 to the n possible truth assignments. Some of the seeds are occupied, so shown in green here. Some are empty, and they are shown in brown. And the problem is to essentially count how many occupied seats we have in this auditorium. And sort of the analogy is that we have a search space for our formula. Some of the assignments are solutions, some are not. They are sort of distributed in this space in an uneven way, and you want to count how many satisfying assignments we have. So the simplest possible approach is to do some kind of brute force counting. The idea is that what you can just do is you can just go through every seat, and if it's occupied, you increment a counter. And of course it's simple, it's accurate, it's exact, but it doesn't scale. If you think about, you can have a giant search space, and of course this is never going to work. So a better approach is to leverage the structure of the problem and to do something sort of DPLL style, if you know what that is. The idea is that we can try to split the space using the structure. For example, divide it into maybe the front versus the back, or the left versus the right. We can sort of try to adapt these partial counts. So for example, we can say, let's divide the space into the front and the back. Let's say how many people are in the front plus how many are in the back. By itself, this is not going to buy you anything, but there are some, you can make it faster if you're using some heuristics, essentially some rules to sort of detect sections that are entirely, say, full or entirely empty. So if you have a way to sort of figure out that, when you're saying, okay, I'm going to say the total number of people is the number of people in the front plus the number of people in the back. Then in the back, I'm going to say is the number of people in this section plus this section plus this section. Now, if you have a way to sort of figure out quickly that an entire section is empty, then this can be much faster than the brute force, but it's still exact. So you're still accounting for every single person in the room, and so it still has scalability issues. So what about approximate model counting? What if we are fine instead of with a reasonably good approximation for the count, but not necessarily the exact number? So the basic approach is to do, the simplest possible approach we can think of is to do some kind of sampling. And the idea is very simple. The idea is that instead of looking at the whole space, what you can do is you can randomly select a subset, maybe one section. You can say, okay, I'm going to count within how many occupied people are there in this section, and then I'm going to multiply it by 6, basically, because there are 6 sections, so I can just multiply by 6. So this is going to be fast, but as you can see, it's not robust at all. You can easily under or overestimate the total count. And we've seen this before. If you have 10 to the 60 solutions in 10 to the 300 seats, it means that this region that you're choosing has to be roughly of the order of 10 to the 240 if you want to hit at least one non-empty seat on average. So again, it's it can be inaccurate, and if you want to make it accurate, essentially you need to choose very large regions, which defeats the purpose of doing sampling. So it's not a good solution. So questions? Good. So now let's move on to and the other major issue is that not only you're not getting accurate answers, but there is no way of knowing if the answer you're getting is accurate or not. That's sort of the thing that perhaps is the most tricky when you apply these kind of techniques. I mean, if you want to build something robust based on this kind of sampling techniques, it's going to be very hard because they don't provide any kind of certificate about the accuracy. Like, you cannot detect. Yeah.
So I'm just wondering about this last point, because I know if you want to like have a population that's divided into people who are voting for one party and another, like I get the impression that there are like if you do sampling and count how many people are voting for one person, somehow they come up with numbers that say, oh, we get these, we think there's this proportion, but with this amount of error. Like,
I think the point is that that's assuming it's a representative sample.
Okay.
Yes. If you could sample from, like one way to do something slightly better than this is to do importance sampling, for example. So the idea is that if you kind of have a rough sense of where people are sitting in the room, then you can sort of try to choose those seats more often than the empty ones. And that can make it work better. The problem is that it's like a chicken and egg problem, figuring if having that kind of importance distribution to begin with is just as hard as solving the original problem. So it's, it's better than this naive sampling, but it doesn't entirely solve the problem.
Okay.
And the issue with those kind of statistics is that, you can come up with, say, you can estimate the sample variance of your estimate. The problem is that in these exponentially large spaces, those guarantees are essentially meaningless.
Okay.
If you think about this problem, like this scenario where you have 10 to the 60 solution and in a space of size 10 to the 300, you're pretty much always going to get an empty seat. And you're going to be, you can do it a billion times and you're still always going to get an empty seat. And so you're going to be, apparently, it seems like, you should be fairly convinced that there is nothing in the space. But the problem is that the space is so large that in order to get something reasonable out of these sort of statistics that you can get by using a small number of samples, you would need basically an exponentially large number of samples in order to be able to say something meaningful.
Okay.
So it's the application you're considering where we have one set of constraints that kind of determine what solutions we even consider, but then we have extra constraints that classify these solutions, and we want to count how the relative size of these classes.
That's sort of but it's just for simplicity. Everything works also for sort of like the weighted case, the more standard graphical model. It's just for...
it's just that we have like 10 to the something large number of solutions that we don't care about, and we don't want to count those at all.
Yeah, that would be... But I mean, mathematically, basically the simplest problem you can think of that is just as hard as probabilistic reasoning is just model counting. I give you a formula, find me all the solutions.
Yeah, no, but like if it's all the solutions to the original question, then like that number will be some 0.00 something, because like...
Oh, that's a fraction, yeah. That's a ratio between two numbers, if you want to write it that way. Yeah. So now let's try something different. And what we're going to do is we're going to implement a distributed coin flipping strategy to count the number of people in the room. So remember, our goal is to count how many people are present in the room. So the intuition for the algorithm we're going to develop is the following one. Suppose we start by asking every person in the room to raise their hand. Then we're going to... Yeah, perfect. Then we're going to ask each person to flip a coin, and with probability 1/2, each person will, say, lower their hand. Perfect. And then we repeat. We again ask every person to flip a coin and lower their hand. And we keep doing that until, say no hand is up, or say one person has a hand up. And then we return true to the number of rounds that it took for basically getting from the initial situation where everybody had their hands up to the situation where nobody has their hand up. And so you can imagine that we start with everybody, everybody has their hand up. Then they flip a coin, some will lower their hand, and they flip a coin, and they keep going. Now, does this work? Well, on average, you can see that this should work, right? Because, if you start with m people, at every round, basically, you cut the number down in half, because roughly half half of the coins will end up being heads, and so you basically cut that number down in half at every round, and so it will roughly take sort of log 2m rounds to get to the point where there is a single hands up or no hands up. And so if you return 2 to the log 2m, you're going to get m. So you're going to get the number of people in the room. That's the basic idea. Does everybody see why this should work intuitively? Yeah?
No, thumbs up for yes.
Okay, good. So the question is, how do we make this into an actual algorithm? How do we get each solution to flip a coin when we don't even know where solutions are? They are sort of hidden in the space, and we don't know anything about the structure of the space. And how do we, we've seen that, roughly speaking, on average, it seems like this should work, but then how do we get a method that has provable robustness guarantees? And it turns out that these issues can all be solved. And what am I doing on time? Okay. So it turns out that a key idea to implement this coin flipping strategy is to use random constraints. So an XOR or parity constraint over 4 variables, A, B, C, and D, is just basically a constraint that is satisfied when an odd number of the variables is set to true. It's just the standard sort of XOR. Or if it's a linear arithmetic modulo 2 if you prefer. So what we're going to do is we're going to start with our original problem, and just for simplicity, imagine that we have 10 variables from x1 through x10, and these boxes up here represent the clauses, the constraints that we have in our original model. And then what we're going to do is we're going to randomly generate a constraint by adding each variable with probability 1/2. So for every variable, we flip a coin, and with probability 1/2, if it comes up head, then we add this variable to the constraint. So maybe we add x1, maybe we don't add x2, then we add x3, x4, x7, x10, then we randomly pick a parity bit. We either choose 0 or 1 for the right-hand side with probability 1/2. And it turns out that each solution will satisfy this additional constraint with probability 1/2. And it also satisfies a strong additional property that is basically saying that given any 2 configurations, so given any 2 assignments to all the variables A and B, the events A satisfies X and B satisfies X are independent of each other. So basically what this means is that this construction implements a strongly universal hash function. So if you think of it as a function that is sort of mapping assignments into 2 buckets, the ones with parity 1 and the ones with parity 0, it's sort of behaving well in the sense that it's roughly putting half of the solutions in one bucket, half of the solutions in the other bucket, and it's assigning solutions to buckets in a more or less independent way, which will turn out to be critical for proving that this method gives strong accuracy guarantees. So the idea is that we're going to now implement the strategy we had before using these parity constraints to implement the distributing coin flipping strategy. So we're going to start with our original formula. We are going to add a parity constraint to sort of throw away half of the solutions. Then we're going to use, say, an off-the-shelf SAT solver to check if the formula is still satisfiable after adding the parity constraint. So checking if there is still a person with their hands up or not. If there is still a person with their hands up, then we have to do another round of coin flipping. So we add another random parity constraint, we check, we keep going, and then basically we conclude something about the model count by saying 2 to the number of rounds that it took for the formula to become unsatisfiable.
When you say random parity constraint, are you talking about in the entire 2 to the n space, or are you talking about
It's over the variables. So if you have n variables, so it's using a small number of random bits to generate this thing.
So that independent statement there, if two configurations are both satisfying, then it's no longer independent.
Satisfying the original formula or the parity constraint?
Let's say satisfying the original formula.
It's still independent. Like it doesn't look at what the configurations are, no matter how you choose them. So these are general configurations. They could either be solutions or not solutions. It will still sort of roughly put half of them in one bucket, half in the other bucket.
So suppose there's exactly two solutions. They differ by one particular variable. If that variable is part of the parity constraint, then it differs between them. If it's not part of them, it's the same, and that's 50% probability.
Yep. And it's independent because we add each variable with probability 1/2. It's actually 3-wise independent, but not 4-wise, I think. But yeah.
Uh-oh.
Yeah. So that's the strategy. And you can see that the key difference from previous methods is that we are changing the formula, but we're still using one of these deterministic sort of reasoning engines that we know are guaranteed to be sound. So because of a theorem that I still haven't shown, but that will basically say that this procedure will give the right answer with high probability, as long as these deterministic reasoning tools that we use in here to check whether the formula is satisfiable or not are sound, as long as we're guaranteed that they will not say that this is satisfiable when it's not satisfiable or vice versa, then this is guaranteed to this will be guaranteed to produce accurate answers with high probability. So it's sort of going in the direction of what we wanted. Sort of the picture to have in mind is something like this. We started with a certain number of solutions shown in green here, maybe 50 of them. Then we add a parity constraint and we throw away roughly half of them. In this case, maybe 22 survive. Remember, it's all based on coin flipping. It's actually implementing that coin flipping strategy we had before. And then we check satisfiability. There is still something left. We add another parity constraint and we keep still satisfiable, another one, until we have, say, a unique solution, and then we know that will roughly take log 2m steps. It turns out that the same strategy can be used for weighted model counting. Remember the situation where we had possible states of the world that are given different probabilities by this sort of more general probabilistic model, where instead of having, I guess it's a wrong slide, but here there should be actual numbers here, and not just true or false, not just 0 and 1s. In that case, how do we do this? How do we compute weighted model counts? How do we sum up the weight of all possible worlds, say such that some property holds, to compute the marginal probability of that event? It turns out that we can still use random parity constraints. They will still have roughly the same effect. So if we have our probabilistic model here that I'm showing so pictorially like this, we have possible states of the world. Each one is given a probability or a weight proportional to the probability. What the random parity constraints will do, if we generate them in the same way, is that they will basically throw away half of the configurations at random. So if we start with something like this, we end up with a probability distribution that looks like this. It's just like what we had before. And it turns out that the right thing to do for weighted problems is almost identical to what we were doing before, except that instead of checking whether the formula is satisfiable at each round, what you do is you find the assignment with the largest weight. So in this case, you find this guy, which is something you can do using an optimization, any kind of optimization tool. You can use it as a black box. All you have to do is to be able to find the configuration with the largest weight that survives after adding the parity constraints. And it turns out that you can still deduce something about the weighted model count, which is what you typically want to do in these problems. And again, the formula changes, but we can still use these optimization tools. So as long as these optimization tools are sound, they give you the right answer, then we're good. And the theorem is that what you can get, basically by repeating this procedure a sufficiently large number of times, you can actually get that with probability 1 minus delta, and where delta is a parameter that you can choose. So say, you can choose it to be 99.9% probability. This algorithm will compute that sum defined over 2 to the n possible states of the world with a relative error that you can make as small as desired. And it will require something like n log n optimization instances. So basically you have to repeat this loop n log n times, where n is the number of variables. And so as long as, there is no free lunch in the sense that these optimization problems are still hard, but if you can't solve these optimization problems, then you're going to get an accurate answer for the original problem.
Does the number of loops depend on the probability?
Yes, I'm hiding the dependency on delta and epsilon, but it's sort of like the standard 1 over delta, good dependency.
Is relative error referring to like the difference in log space?
Different in which log space?
Like the log of the number of solutions. Like you have a real number of solutions in your estimate. Are you saying that
it's multiplicative? Yes. So it's additive in log space. Yes. Yeah. So the good thing is you get strong accuracy guarantees. You can plug in off-the-shelf optimization tools that we know are that sometimes that can provide certificates of optimality. So if you have a certificate of optimality for the optimization problem, that becomes a certificate of accuracy for the probabilistic reasoning problem. And even when we cannot solve these problems to optimality, sometimes these optimization tools can give you bounds. They can say, I cannot solve this optimization problem exactly, but I know that the optimal number is smaller than some bound. It turns out that you can use these bounds and plug them into the counting problem, and you can get bounds on the probabilistic inference query. And then you can parallelize easily. Each one of these problems can be solved independently, so that's nice sort of computational. So this is just an example showing that how existing techniques can go really bad. This is an Isaac model from physics. I'm showing as a function of the number of variables, sort of like the log of the partition function estimated by different techniques. So in blue, I have ground truth up to about 25 variables, which is what you can do using brute force. In blue, I have the estimate computed by this technique, and there is a small error band here. You don't see it very well in this scale, but that's basically what the theorem says. With probability 99%, ground truth is going to be within this error bar. And in fact, you see that it is the case up to here. And we don't know exactly what ground truth is for these points, but we know it's going to be within these bars with high probability. And you know that existing techniques can give very inaccurate answer. It can be off by hundreds of orders of magnitude, and it's hard to know whether they're off. They don't really. Well, sometimes you know that you have a lower bound, but you never know basically how far you are from the true answer. So this technique is more expensive computationally, but it gives you this nice sort of theoretical guarantees. What am I doing on time? So similarly, this is for computing, let me go quickly, for computing marginal probabilities. It turns out that, again, you can do pretty well. I wanted to move on to some of the newer stuff, maybe. So there are several people that have been working on this idea, several different implementations. An interesting question is that of understanding how hard these optimization problems or these search queries are when we add the disparity constraints. And it turns out that it has a lot to do with how long disparity constraints are, how many variables they touch. If disparity constraints only touch one variable, then they're pretty easy because we're saying we're fixing the variable to one particular value. The problem is that they won't work well for our counting purposes. And on the other sort of end of the spectrum, we know that if we add each variable with probability 1/2, this will give accurate counts. With high probability, everything will work great. But empirically, these problems are harder to solve because they involve more variables. And so the question is, what happens in between? What's the trade-off between the hardness of solving these problems versus the statistical guarantees that we get on our estimates? And so we would like our constraints to be short so that they are easier to reason about, but we would like them to be long because that will give us better guarantees on the counts. So natural question is whether we can use something in between. Is this the best we can do, or is there something in here that would actually work? So practically what we would like to do is, instead of adding each variable with probability 1/2, we would like to add each variable with some probability much smaller than 1/2. For example, instead of adding a lot of variables, maybe we only add x1 and x7, because that's an easier constraint to deal with. So before, remember, we were adding each variable with probability 1/2. We don't want to do that. We actually want to add each variable with probability. We want to generate sparse constraints, low density constraints. So remember that we're doing these parity constraints because we want to implement this distributed coin flipping strategy. And ideally, we would like each configuration to flip a coin independently. So maybe, you get heads, then the second configuration flips and get tails, and then, another heads. This is the kind of strategy we want to implement. Get people to flip coins and then throw away half of them. Throw away all the tails, say, and keep only the heads. The problem is that we cannot generate so many independent coin flips. There are 2 to the n possible configurations, and so it would sort of require too much randomness to do that. So instead, what we did with the parity constraints was to have each solution flip a coin, but these coins are not going to be fully independent, they're going to be only pairwise independent. So given any 2 of them, they will be independent, but if you look at 3 or more, they might be dependent on each other. And it turns out the intuition is that with pairwise independence, we can still guarantee that basically stuff does not cluster too much in a single cluster. There is enough randomness that they will roughly be split. They will be split in a more or less random way so that we can still get our guarantees. And the key thing is that there is this randomness amplification argument that basically tells us that, which seems magic, but it turns out that you can simulate an exponentially large number of pairwise independent coin flips, 2 to the n pairwise independent coin flips, and you can generate them and represent them in a compact way using a single parity constraint, which only required n bits to generate. So that's sort of the power of this argument. Now, the problem is that long parity constraints are difficult to deal with. So one thing we looked at was to what we call an average universal hash function. And it is that we're not even guaranteeing, we want to generate a class of hash functions, of parity constraints, such that pairs of coin flips are not guaranteed to be independent anymore. But instead what we're going to say is if you look at sufficiently large sets of coins, and if you look at all pairs within this set, on average, they're going to be roughly independent. And it turns out that this is sufficient to get all the kind of nice guarantees we had before. And the beauty of this is that it can actually be implemented with short parity constraints. So it turns out that to get these parity constraints of length log n are both sufficient and necessary. So before we were adding each variable probability 1/2, so we had a length of n over 2. Actually log n is both necessary and sufficient, and you get the same accuracy guarantees. This is based on some sort of powerful ideas from the theory of low density parity check codes. These kind of constructions where you have random parity constraints. I don't know where they are, but well, random parity constraints are used a lot in information theory to build error correcting codes, and some of those ideas can be used to actually prove this result. Yeah.
Would selecting log n variables as a n choose log n thing have the same properties?
Yes, but it's trickier to prove because of some weird odd even stuff that messes up the proofs, but yes. So this is just one example showing as a function. How much time do I have?
So we set aside an hour. You've only talked today, so if you go over a little bit, it's fine.
Okay. Yeah, I think I have a few more slides, but this is just showing how sparse parity constraints can actually lead to much faster computations. And it turns out if you use sparse parity constraints, you're going to get basically lower and upper bounds on the true model count. And sort of the sparser the constraints you use, the looser these bounds become. But then we basically proved that at some point, for a certain length of the parity constraints, this upper and lower bound, they sort of reach within a factor of each other. We can prove that basically they get close to each other. And computationally, basically, you can get pretty good results much faster. This is in a log scale. It's showing like the log scale, the upper bound on the model count. This is in log scale, the computation time. So using sparse constraints, you can get much quicker, reasonably good answers. Now, another interesting question is whether you can use different types of constraints that are not parity constraints. And the idea is that we would like to take any function of some input, say A, B, C, and D, some kind of circuit, and we would like to somehow generate a random constraint by randomly wiring some of the inputs, so the input variables, to this circuit, so like what we were doing for the XORs, and randomly picking a output value for this function. So in this case, we would say that f of not x1, not x3, not x3, not x2, not x4 equals 1. Like before, we were using f, our function f was an XOR, but what if you use a different function here? What if you generate a random constraint based on a different function, like A and B or C, for example? Would that work? And one of the recent things we did was to show that this would actually, we were able to analyze how well a general function would work as a hash function. It turns out that a key property that determines how well a function works as a hash function is the noise sensitivity, which is basically a property of a function that will tell you how likely, how sensitive the value of the function is to noise. So the definition is that you randomly pick an input for a function. Let's call it x, say maybe 0, 1, 1, 0. You randomly flip each bit of the input with some probability p, and you get a new input, maybe 1, 1, 1, 0. And then you check how likely is it that the value of the function stays the same or it changes. So if a function is very noise sensitive, then if you change one bit, then the function is likely to change value. And while if the function is, say, a constant, then it doesn't matter. Even if you change bits, the value of the function doesn't change, and so it's not noise sensitive at all. And it turns out that you can actually show that there is a direct relationship between the noise sensitivity of the function and how well the corresponding family of hash function will work. And the more noise sensitive a function is, the better it will behave. And so it turns out that the noise sensitivity is a property that you can compute in closed form by looking at the Fourier spectrum of the function. And sort of the intuition is that you want these functions to be have a very oscillatory nature, because if it looks like a sine wave that looks like this, it's not like it has a lot of bumps, then you can imagine that by changing the input a little bit, the function will change. It's very likely to change. So sort of, the Fourier basis for discrete functions are actually XORs. So that sort of ties together to why we were using XORs, because XORs are sort of the most noise-sensitive function you can think of. It's something that looks like this. As soon as you change one bit, the XOR will change, which means that it's very noise-sensitive, and that's why it works well. But again, as we knew, you can actually use short XORs, and it turns out you can use other functions as well, as long as they are sufficiently bumpy, as long as you know basically something about their Fourier spectrum. And so basically you can even change this algorithm where you can now put in any kind of random constraint here, and we'll be able to tell you something about the model count at the end. I think this is pretty much what here's an example of sort of using a function known as tribes, which are basically disjunction of conjunctions. People have been studying this kind of noise sensitivity issues in computational social choice theory to study voting systems, like how likely is the outcome of an election, like how much is the outcome of an election influenced by every single vote. That's kind of the noise sensitivity. That's why it has been studied in that literature. So tribes are one such function that has some good properties in terms of noise sensitivity, like it's the most noise sensitive property in some restricted class of functions that are easy to deal with. Turns out that they are much faster to deal with and they give good bounds. So I guess let me skip this part. I had some, turns out you can actually plug in this stuff into variational inference. You can actually get guarantees in variational inference problems, but let me skip that and let me move to the conclusion. So I think the high level idea is that we know in the deterministic reasoning world, we have these solvers like SAT solvers, integer linear programming solvers that are always guaranteed to give the right answer. People care a lot about that. In the probabilistic reasoning world, people have cared more about scalability than accuracy. And, we've been making some progress in terms of developing these new techniques that can take a probabilistic problem and reduce it to something deterministic that we know how to deal with. So that if you have deterministic solvers that will give you certificates or can provide proofs of correctness, then you can sort of leverage all these ideas in the probabilistic reasoning world. There is still a lot more to do, like dealing with continuous variables, more general classes of theories, not just propositional, understanding the trade-offs between accuracy and runtime. But sort of the dream is to come up with, that green box that we had in the scheme at the beginning, come up with a general purpose probabilistic reasoning engine that is both scalable and accurate. Like ideally something where you have an input parameter that controls how accurate your answer is going to be. And you can set it, but you know that the answer you're going to get is really what you want and not just some number that is hard to interpret otherwise. That's it.
Thank you. So we have time for a couple of questions. So, am I right that this method gives you just the order of magnitude of the model count rather than giving you sort of any better than a Fermi estimate?
It will give you can get it up, it's some multiplicative, like you can get within a 1 plus epsilon error, multiplicative. But epsilon can be made as small as you want.
Okay.
But you have a price in terms of...
But it would be more efficient as sort of like anomaly detection than as like Bayesian inference.
Well, why would you?
Anomaly detection, you want to just say, is it bigger than some small threshold? Bayesian inference, you might want to say, can I get some precision on the digits of this?
Yeah, you can. So there are sort of two answers. If you actually want to, as usual, as most of these techniques, like the bounds are very pessimistic. So maybe you can prove that the answer you're going to get is within a factor of 2 or within a factor of 1.5 or 1.0001. In practice, actually, it's always way better than that, both because there is just some sloppy bounding in the proofs, and also because that's assuming sort of the worst possible distribution of the solutions in the space, that is sort of like making it as hard as possible for our constraint to sort of break them up into buckets. In practice, results are always a lot better than what the theory predicts as expected. So that's, I guess, would be another potentially interesting direction to explore, is making the analysis tighter, because we know that right now it is not. But I think you could definitely use it in the, like we've used it to do model comparison. Like, you have two undirected models and you need the partition function to figure out which one is better, or you want to stop training to detect overfitting. We've used this in that context. So I guess that would be more the Bayesian side.
Thanks.
Yeah. Yeah.
So, did you notice a phase transition or something when you got probability proportional to log n over n, or?
Phase transition in what sense? Like in the hardness of the?
Like you had a couple of things you were optimizing for. I was just curious if this was very tightly specified as being exactly like log n variables because of some phase transition.
Oh, yeah.
Or did you just find that it happened?
There is a very interesting phase transition. Basically, what we're doing is we're generating a random binary matrix with each entry is like chosen independently, like it's like a Bernoulli random variable. Is there 0, 1 with probability p? And it turns out that if you have like an n by n matrix, and that probability p is of order log n over n, that's the right ratio such that the matrix is full rank with probability 1 in the limit.
Okay.
So there is like that phase transition if the probability is higher than that threshold, then the matrix is going to be full rank with probability 1 basically. And if you are below that threshold, then the matrix is going to be low rank. And that's basically where it comes up.
Okay, cool. Another question. In your diagram where you kind of went from the solver, then kind of back and generated some new random constraints, would it be possible to generate constraints not fully at random, but slightly informed by what parts would make future iterations of the solver easier, or will that break all of the independence?
That's a great question. I think you could do something there. We haven't explored much that, but I think you can. It would sort of, in some sense, what we're doing is some kind of. You could think of doing something like kind of like importance sampling, where by knowing sort of what kind of bias you put into selecting the way you split stuff into buckets, then you account for that. And right now we're doing it uniformly, which is hardly the best thing. But then it makes the proofs easier, but I think you could potentially work something out. Yeah.
Could you use binary search to find the time where everyone has their hand down?
Yes.
You are doing that?
I think there is a paper at each Chi coming up where they basically that's their contribution. They already done it, sorry. Yeah.
I was really confused about how you do the thing with the weights, because it seems like you can have a situation where in the bucket there's like a few with really high weight and like a bunch with really low weight. It seems like you have to account for both. I wasn't sure like how you do that.
Yeah, so when you have weights, it's not like you just stop when it becomes empty. Like you sort of have to go all the way, and you have to sort of sum them up based on the kind of, the idea is that, so ideally one strategy could be to sort of divide everything into 2 buckets, estimate the weight in 1 bucket, and say multiply by 2, right? Problem is that estimating the weight in 1 bucket it's still hard. It's still a counting problem. But it turns out that after hashing a sufficiently large number of times, basically you're guaranteed that you can approximate the weight in 1 bucket well just by taking the mode, just by taking the largest element into that bucket. The intuition is that if sort of the distribution of weights within the bucket is more or less uniform, then splitting again would work. Because, so this can go imagine a situation where everything has weight 0 and one thing has weight 1,000. If you split into 2 buckets, this is very risky, right? Because one bucket might get nothing and the other one gets everything. So this won't work. You might imagine that this wouldn't work. But the thing is that in that case, basically by taking the mode, by taking the largest element at every iteration, we're sort of making sure that are protecting us against that situation where there is a single element that has a very large weight compared to everything else. While if the problem is with just taking the largest element is that it's possible that maybe everything has the same weight, right? And then taking the largest element would be a terrible approximation for the total weight. But in that case, by splitting into 2 buckets would essentially always work, because if everything has the same weight, then the 2 buckets will get exactly the same weight, and so the approximation is perfect. So by doing both the splitting and taking the maximum, you're sort of protecting against, you're sort of hedging against both extreme cases, the one where you have a uniform distribution and the one where you have like a direct delta kind of distribution. And by using both of them at the same time, you can actually show that it will work no matter what the underlying distribution is.
All right. So let's thank Stefano one more time.
Thanks.